Once it was shown that a bomb made from highly impact-resistant materials could penetrate over 6 meters of reinforced concrete and explode on the other side while staying nearly intact, underground bunkers quickly became obsolete. No set or arrangement of thick reinforced concrete walls could prevent or stop a successive attack by bunker busters, which is what this type of wall-penetrating bomb is known as. Even underground nuclear shelters, buried many meters deep and built for important people like presidents, were not considered fully safe from this type of bomb. They were continuously being improved and enhanced, and are even capable of counting the floors as they pass through them, being able to explode only on a predetermined floor. But as in any war, when one side improves its strategy, the other quickly adapts too. And in this case, it was always a contest between improvements in bomb construction and improvements in bunker construction. And this time, it seems that underground shelters or bunkers are ahead with the emergence of a new type of concrete. So a bunker buster can penetrate walls or reinforced concrete over 6 meters thick. A lot of science is behind it. Everything centers on two principles: hardness and resistance. The hardness of the weapon to penetrate through the concrete, and the resistance of the concrete to withstand the force or impact applied to it and still maintain its structural integrity. And you have to be very careful with the word hardness, because hardness is a very well-defined concept in material science. Hardness can be defined and measured by a material's ability to penetrate another. To better understand what hardness is, let's take diamonds as an example. Diamond is the hardest natural mineral, with hardness meaning its ability to scratch other minerals. Diamond scratches glass, quartz, sapphire, ruby, and all other minerals, but it can only be scratched by another diamond. This characteristic is why diamonds are used in some blades and saws for cutting stone. But although diamonds are the hardest, they are nowhere near the strongest. Strength is a clearly defined concept in material science. In other words, although they are hard, they are not strong and break easily, or in other words, they are not suitable for purposes that involve high impacts. Newton himself proposed an approximation equation for the penetration depth of a projectile moving at high speeds, considering only momentum. In simple terms, the theory says that the greater the density of the penetrating projectile compared to the target it is meant to penetrate, the deeper the projectile will penetrate. This theory suggests a 2.4 meter uranium projectile with a density of 19 grams per cubic centimeter can penetrate 6 meters into solid steel walls. The theory overlooks key factors like the material's hardness, resistance, and how kinetic energy is dissipated on impact. For example, a bulletproof vest made of Kevlar is hit by a projectile. Since the projectile is denser than the Kevlar layers, it should theoretically pass through the vest easily. However, Kevlar's thin layers are tougher than the bullet's material. This allows the Kevlar to absorb the tremendous kinetic energy of the bullet, bringing it to a complete stop without the Kevlar fibers breaking. But if the bullet is made of a much harder steel, now the projectile can go through the Kevlar much more easily, because the projectile now has a higher degree of hardness than Kevlar. If the vest is made of plates of a much harder metal, the impact will cause the projectile to disintegrate. If we put tungsten at the tip of the bullet, which is one of the hardest metals that exists, it will cause the plates to shatter and break on impact. That's because, although the plates are hard, they are not as hard as tungsten. They will break and fail structurally under impact. So, drilling through walls using bombs specially made for this purpose isn't just about speed and impact force. The material the bomb is made of makes all the difference in the impact. And it makes all the difference for the bomb to be able to go through thick reinforced concrete walls and still remain almost intact after passing completely through them. During World War II, these concepts were poorly understood. It was believed that a bomb only needed to be extremely large, heavy, and made of a durable material to penetrate deep into the ground or thick concrete walls. This led to the creation of the Grand Slam, the largest bomb used in World War II. A 10-ton bomb, 8 meters long and just over a meter in diameter, dropped from a great height by a bomber. The Grand Slam featured a tail rocket motor that, when fired, boosted its fall speed to around 1,600 km per hour. The bomb was so powerful it could penetrate 6 meters of reinforced concrete or burrow 40 meters underground before detonating. By the way, one of the main features of the bomb was to use its enormous kinetic energy from the impact to propagate powerful shock waves underground, which would severely destroy any building near the impact zone, including the target itself if the bomb hit it. Referring to Newton's approximation equation, its improved version, the Jansz equation, shows that maximum projectile penetration occurs when the projectile is thin, long, very dense, and strikes at extremely high speeds. And that's why in World War II we had the Grand Slam weighing 10 tons, which did a good job of penetrating. However, in the 21st century we have the Guided Bomb Unit 28, which weighs only 2.2 tons with a much thinner and more compact design, but much denser. The Guided Bomb Unit 28, measuring 40 centimeters in diameter and 5.7 meters long, can penetrate 6 meters of reinforced concrete or 30 meters underground. In other words, it can penetrate in a way very similar to the Grand Slam. That's called evolution. It's longer, but its thinner, more compact design focuses kinetic energy on a fine point, making it easy to pierce concrete. Reminder: these bombs are meant to penetrate special, not ordinary concrete, which is easy to breach. It's a much harder, stronger and more resistant concrete, specially modified in labs. It can withstand heavy impacts without structural failure and is highly resistant to compression loads. And that's why they're used in the construction of underground bunkers. Only 2 Guided Bomb Unit 28 bombs were used during Operation Desert Storm, one of which missed the target and the other hit one of the bunkers directly. 2 days later, Iraq surrendered in the face of the destructive power of the new weapon, faced with its bunkers considered impenetrable. Although the new bunker booster bomb design, thinner and more compact, has its advantages, the penetration and destructive power of the older, larger, heavier and wider bombs cannot be underestimated. If the structure of a modern bunker is hit directly by a very heavy, large diameter, high hardness and high speed bomb, the impact force and shock generated will be so great that, in addition to penetrating the wall, it will propagate powerful waves with the potential to severely compromise the structural integrity of the building. And that's why the Massive Ordnance Penetrator exists, or Massive Ordnance Penetrator, a bomb introduced in 2013 weighing 14 tons, 6 meters long, 80 centimeters in diameter, and containing 2 tons of explosives. It's the largest bomb in its category. Both the Massive Ordnance Penetrator and the Grand Slam are made from a steel known as Eagle Steel, a high-performance, extremely strong steel developed by the United States Air Force. This steel contains a bit of carbon, a little nickel, and traces of tungsten, chromium, magnesium, vanadium, among other elements. They all enhance the alloy's strength. In fact, Eagle Steel is more than 6 times stronger than the steel used to build buildings. Things went well until early 2008. In the late 2000s, a rumor spread about an Iranian bunker struck by a bunker buster bomb. The bomb failed to penetrate and became embedded in the bunker's concrete, inexplicably stopping instead of passing through. This surprised American analysts in the field. The reason for this is that Iran is a leader in the development of something known as ultra-high performance concrete, or ultra-high performance concrete. Ultra-high performance concrete is not just a new type of concrete. In fact, experts have turned it into a composite material. Ultra-high performance concrete uses ordinary cement, supplementary cementitious materials, quartz flour, among others. In addition, 1% of high carbon fibers, carbon glass, or a combination of these is added. This works so well that ultra-high performance concrete has high levels of durability, ductility, and hardness. To give you an idea, the compressive strength of ultra-high performance concrete before fracturing is 200 MPa, while that of regular concrete ranges from 20 to 25 MPa. Because of these concrete improvements, the MOP has already been updated 4 times before starting operations. The MOP can penetrate up to 61 meters in regular reinforced concrete, but only 8 meters in lab-modified concrete bunkers. And it drops to around 2 meters in structures made with ultra-high performance concrete. When a piece of concrete is hit with great force, 2 scenarios can occur. The first is that the strong impact will cause the concrete in the impact zone to break, and at the same time several cracks spreading from the impact zone will propagate, leading to the total breakage or collapse of the concrete. This happens because concrete handles high compressive forces well, such as supporting buildings, but is fragile under impacts or stretching. Although it broke, it absorbed part of the kinetic energy from the impact. The second possible scenario is that if the piece of concrete is very strong and thick, all the kinetic energy from the impact will be absorbed and the projectile will be stopped, without the concrete breaking or cracks spreading from impact. In other words, a major flaw of regular concrete is its inability to withstand large impacts and its tendency to crack. And this is where the ingenuity of ultra-high performance concrete and the 1% of fibers added to it come in. Besides being much harder, these fibers help prevent cracks from spreading. So, when it receives a strong impact, it absorbs a lot of the kinetic energy from the impact and greatly limits the appearance of cracks that would compromise its integrity. Additionally, its density makes penetration much harder. Although this new type of concrete will significantly reduce the penetration power of current bunker busters still remain an imminent threat. Several modifications can be made to the bomb to improve its penetration. Dr. Todd Snyder, who helped design the guided bomb unit 2080's penetrating tip, did his doctoral thesis on it, exploring how different types of grain arrangements in a metal improve and increase its resistance to deformation. That's because, in general, materials are hard or strong in certain directions and brittle in others. In addition, bomb tips made of tungsten, depleted uranium, or an arrangement of both with improved designs, higher speed bomb terminal, adding a small rocket motor to the tail to increase impact speed, among other things, greatly improve the penetration power of these weapons. However, nowadays this type of bomb is numbered, at least in its current versions. That's because the trend is to build bunkers deeper and deeper underground, and its limitations in launch dynamics and penetration power may not be enough for the current reality. An example is one of the Iranian missile bunkers, which was built just 500 meters underground. Remember, the MOP can penetrate up to 61 meters underground. But the military world is full of surprises. You never know what the other side has up its sleeve.